Hello and thanks for listening. This is video 2 of Unit 3 and it's going to cover association rules. So this is going to be the first video that actually dives into one of our methods for unsupervised learning. So this is beneficial because it is used very frequently in industry, so we really want to understand association rules, and it's a great example of unsupervised learning because we don't really have that output. And so let's dive right in and see what this entails. And once again, this is presented by EDU Onyx. So the goal of association rules is to find joint values of the variable x, our input, that appear most frequently in the database. So that's kind of hard to understand, so maybe we can explain on that a little further. An association rule is going to be an implication of the form if x then y, where x is the antecedent and y is the consequence of the rule. So when we refer to antecedent from here on out, we're talking about the input, and y is going to be our consequence, what we get out of that rule or that association. This is most often applied to binary value data, where it is referred to as market basket analysis. In this context, the observations are going to be like sales transactions, such as those occurring at the checkout counter of a store, and we want to find the dependency between two transactions, X and Y. So this information can be quite useful for stocking shelves, cross-marketing sales promotions, catalog design, and consumer segmentation based on these buying patterns. So we're going to use market basket analysis as our example of association rules throughout this video. And in association rules, again, are almost always used in market basket analysis. This is the primary application of these rules, and it's a big one, so it's important to cover. So if we have our implication of the form if x then y, it's important to note that y as well is not an output that we are supplying this algorithm with. It's simply a consequence of whatever rule we are making about our input data. So for example, we might have something like, if a consumer buys the object X, let's say bananas, they are very likely to also buy Y, the milk, where both the bananas and milk are inputs into this algorithm. So let's keep going, and hopefully this will become a little bit more clear as we move forward. So association rules are really understood through these different measures. So the first two that we're going to cover are support and confidence. So support of the association rule, if x then y, is going to be based on the probability distributions of x and y. So the probability of x and y, denoted here in this first equation for the support, in our example of market basket analysis, is going to be the number of customers who bought x and y divided by the total number of customers. So this is just the probability of x and y occurring. Meanwhile, confidence of the association rule, if x then y, is going to be defined by this probability of y given that we have x. So this is how likely are we going to get y if x has already occurred. So to calculate this, we have the probability of x and y divided by just the probability of x. So in our market basket analysis, this is going to be the number of customers who bought x and y divided by the number of customers who bought x. So confidence is the conditional probability, which is what we normally calculate. To be able to say that the rule holds with enough confidence, this value should be close to 1 and significantly larger than just the probability of y alone, the overall probability of people buying y. And then we are also interested in maximizing the support of the rule, because even if there is a dependency with a strong confidence value, if the number of such customers is small, the rule is worthless. So support shows the statistical significance of the rule, whereas confidence shows the strength of the rule. So the minimum support and confidence values are going to be set by the company, and all the rules are going to have these different values. So whoever is generating this algorithm can decide what's the minimum amount of support and confidence I want to have for my association rules to show that they are both statistically significant and also strong and have a lot of validity to that rule. So the third measure for association rules that we are going to cover and gets used almost exclusively is the lift of the association rule. So if x and y are independent, then we expect lift to be close to 1. So this is no dependency between the variables. If the ratio differs, that is, if the probability of y given x and the probability of just y alone are different, we expect there to be a dependency between the two items. If the lift is more than 1, we can say that x makes y more likely, and if the lift is less than 1, having x makes y less likely. So in our example where we had bananas and milk, if we had a large lift between those items, like let's say a lift of 2 or 3, we could be able to say that buying milk makes buying bananas more likely, or vice versa, buying bananas makes buying milk more likely. If we had a lift less than 1, we would say it makes it less likely. So maybe if the lift was like 0.5, we could say buying milk makes you less likely to buy bananas, although I would expect that that rule would have a large lift because it seems like those two products go together. So this is the 3 measures for association rules that we're going to use, and support, confidence, and lift. And these are really the only ones that you do need to know to apply association rules. There are other measures out there, however, they're used much less commonly than these 3. So we've been talking about two variables, just 2 items. What if we want to extrapolate that information to more than 2 items? And we can do this using the a priori algorithm. So these formulas can easily be generalized to more than 2 items. So for example, if we have a 3-item set, we may look for a rule such that is written like this. If we have x and z, then y, or x and y, then we have z. That is the probability of z given that we have x and y. And so we are going to be interested in finding all such rules having high enough support and confidence. And because the sales database is generally very large, we want to find them by doing a small number of passes over the database. So this algorithm exists, and it was developed in 1996, and it's called the a priori algorithm, and it does this in 2 steps. It starts by 1, finding frequent item sets, that is those which have high enough support, and then 2, converting them to rules with enough confidence by splitting the items into 2 as items in the antecedent and items in the consequence. So this algorithm is going to look for all item sets, all groupings of items that go together, and then try to split them into an antecedent and a consequence and return those that have enough confidence. And again, so that support level and confidence level are going to be set by whoever is developing the algorithm to look for these items. So again, here are those 2 steps. We start by 1, finding frequent item steps, those with enough support. And then 2, we convert item sets into rules by splitting them into an antecedent and consequence and checking the confidence and lift for each of those antecedent and consequent pairs. So this is a very useful algorithm, and it's generally going to be the one you use if you're looking for more than just 2 items in each item set. So this gets used all the time and is going to be the most common application of association rules. So we also need to talk about hidden variables, because it should be kept in mind that a rule like if x then y does not need to imply causality, but just an association. In a problem, there may also be hidden variables whose values are never known through evidence. So the advantage of using hidden variables is that the dependency structure can be more easily defined. So let's talk about this through an example. If we were looking at a problem of basket analysis and we want to find the dependency among items sold, we could have a dependency among baby food, diapers, and milk, and that the customer buying one of these is very much more likely to buy the other 2. So instead of representing dependencies among these 3, we may designate a hidden node, such as a baby at home, as the hidden cause of the consumption of these 3 items. When there are hidden nodes, their values are going to be estimated given the values of observed nodes and then filled in. So this is really going to be the only time we touch on hidden variables, but it's just really important to know that these association rules do not imply causality. So buying milk does not cause you to buy more bananas. They are simply associated together. So let's take a look at a basket analysis example, and we're going to do so by considering the following transactions. So we only have 8 transactions here, so very small input set. However, we have a variety of different products being bought. We are going to look at the dependency between beer and apples and see if we can come up with anything for that. So we see those occurring together in a fair amount of these transactions. So we might think that there would be a connection between the two. So let's go ahead and calculate our 3 measures, being support and confidence and lift, and see if we can actually mathematically show an association between these 2 items. So we're going to start with the support, and this is going to be the first step in learning the association between apples and beer. The support is simply going to be for the support for apples, the probability of apples. There were, if we look back, 4 transactions out of a total of 8 where we got apples. So this is just going to be a support of 0.5. 0.5, it's fairly significant, so we're going to go ahead and say that there is statistical significance behind this, so it's worth pursuing. And then we move to the confidence. So the confidence is going to be the support of apples and beer divided by the support of just apples alone. And so to calculate this, we see that 3 out of 8 times apples and beer are bought together. And then we're going to divide that by 1/2, just the support of apples alone. And so we get 75% confidence. So not only is this statistically significant, but there is strong strength between these 2 items. But let's move on. Let's look at the lift. So this is going to be calculated as such. We have the support of the apples and beer divided by the support of apples and beer alone. So this is going to be looking for a dependency between these objects by taking into consideration the probability distributions of simply beer and apple occurring. So this is calculated as such. Again, we have 3 out of 8 times apple and beer are bought together. 4 out of 8 times the apples are bought, and then 6 out of 8 times actually beer is bought. And this ends up coming out exactly equal to 1. So unfortunately, despite the statistical significance and the strength of the rule, there is no dependency between these items that we can see, at least in these 8 transactions. So buying apples does not make you more likely to buy beer, and buying beer does not make it more likely for you to buy apples. So unfortunately, no dependency here, but still useful data. And so that's just a quick easy example of an association rule. The a priori algorithm is going to sort through your entire database, all of your transaction data, and try to look for some of these rules. And then you can use those in your marketing. So this is association rules in a nutshell. Just a quick video to introduce the topic. And these are used almost all the time in different consumerist applications where the company wants to use it for stocking shelves or cross-marketing, sales promotions. So really good to understand association rules. Actually very easily implemented because you're not going to develop the new algorithms yourself. You're simply going to use a priori algorithm. However, you're going to set your own support and confidence levels that you want to look for in your rules. So that's association rules. Our next video is going to be on cluster analysis. And cluster analysis is actually going to be the bulk of unsupervised learning, in my opinion. And so we're going to look at some of the math behind cluster analysis and some of the applications as well. So thanks for listening, and I'll talk to you guys soon.